Thanks everyone for attending today's machine learning seminar. Today we're fortunate to have Professor Robert Nowak from Wisconsin-Madison to give the seminar. So I'll start with a very brief introduction and then we'll start the talk. And during your talk, please feel free to send your question at the question box. There's a Q&A, so I'll monitor the question in case there's anything you want to ask. Feel free. All right, so Professor Robert Nowak is a McFarland Bascom Professor in Engineering at University of Wisconsin-Madison, where his research focuses on signal processing, machine learning, optimization, and statistics. He is a professor in electrical and computer engineering, as well as being affiliated with the departments of computer science, statistics, and biomedical engineering. He is a fellow of the IEEE and Wisconsin Institute for Discovery, a member of the Wisconsin Optimization Research Consortium, and Machine Learning at Wisconsin. He is also an adjunct professor at the Toyota Institute, Technology Institute at Chicago. Okay, so without much further ado, let's welcome Professor Rob Nowak to give a wonderful talk. Virtual applause.
Great. Thank you. Thanks for that great introduction. Thank you to all the organizers. So I'm going to talk about active learning, and I want to give you a little bit of a tour all the way from, actively learning linear classifiers to all the way to learning overparameterized neural network classifiers. And I'll kind of explain everything as we go. And I just want to mention this is joint work with Mina Karzan, who's a postdoc or was a postdoc with me. She's now at the Toyota Technological Institute at Chicago, and she'll be joining UC Davis in about 12 months from now, and Rahul Pari, who's a graduate student at the University of Wisconsin. I assume my slide transitioned properly. If not, somebody speak up and let me know. So this slide here, I just want to, first of all, introduce and motivate the idea of active learning. So to begin, I want to talk about the conventional, what we call passive machine learning pipeline. And the idea here is that we have a large set of unlabeled raw data. We're going to ask a human expert or a group of experts to label that data for us. And then we're going to turn that labeled training set over to a machine learning algorithm, which will produce a predictive model. And so I think everybody's familiar with this pipeline, but it would look something like this in the context of image classification. We have a bunch of images that we just collected off the internet, say. They're unlabeled, so we're going to have a human expert label these dogs, boats, etc. And then we're going to train our machine learning algorithm. Maybe it's a deep neural network parameterized by some weights W that yields a function f sub w that we can use to predict and classify the labels of new unlabeled images. Okay. So this has been a great success. We all know about it. We can have computers recognizing images as well as humans. They can translate from one language to another. They can master games better than humans. But under the hood of all these engineering accomplishments is a lot of human effort in many cases. So for example, millions of labeled images from humans in the case of image classification. In text translation, they're using bodies of text, for example, from the United Nations or something that have been painstakingly translated by humans, and then the machines are trained on those translation pairs. And in game playing, the machines are playing more games than even my son could stomach. So there's a big kind of difference between maybe how machines are learning these days and how humans like my son learn. And also there's a huge human effort in a lot of these design of these machine learning systems. And so we'd like to think about how can we train machines with less labeled data and less human supervision. And this is a super active area of research. There's a number of different approaches ranging from things like self-supervised training to things like active learning. And I'm going to focus on the active learning idea, which I'll illustrate with the same kind of scenario again. So this was the original pipeline. The idea in active learning is essentially to add an additional component to the machine learning system. We call a data selection algorithm. And what this component does is it looks at the current model learned by the machine, uses that model to decide which examples it would like that human expert to label. In other words, the machine learning algorithm is sort of asking for help. Maybe it's very confident in its predictions of certain examples, but has less confidence in others. And it's on those less confident examples that it might ask the human expert for a label. So the idea is the machine automatically and adaptively selects the most informative examples for labeling, and this reduces the time and effort of human supervisors in this training process. Okay, so I hope that's clear to everybody. I'll kind of illustrate it in a minute with a concrete example, but I just want to point out that, I'll mention, I've been working on this sort of problem of active learning for, maybe almost 15 years now. And when I started, of course, it was something that was really mainly in the academic world and largely theoretical. But more recently, this has really come up in services that you can purchase. For example, Amazon has a service called SageMaker Ground Truth, which does exactly what I was saying. Data is only routed to humans in the active learning system if it can't accurately label it itself. Prodigy is another company and service which uses active learning to annotate large data sets. So this is something that's a real issue, a real challenge in modern machine learning AI systems, and that is, how do you get the labels in your training data set? Maybe you should do something systematic and efficient like active learning. So here's one example that we've looked at a little bit at Madison. And so this picture emphasizes one feature of active learning, which is that it's sort of a closed loop approach to machine learning. And in this particular application, the idea is we want to train a machine to automatically look at electronic health records and then decide whether or not a person is likely to get a disease or maybe even has a disease based on all the information in their EHR. So human experts need to provide labels to the machine learner. A labeling of just a single EHR could take several minutes, so it's a very time-consuming process. Also, these experts get paid, $100, $200 an hour. So these are very expensive labels to collect, but that's the idea. Human experts label these electronic health records, or a subset of them. Those are turned over to the machine learning algorithm. The machine learns a rule. That rule can be applied to new unlabeled electronic health records, and then the active learning component is to select from that subset of unlabeled records some that it needs help with, and turns those over to the human experts for labeling. So to illustrate this a little bit graphically, let's just suppose that we had two electronic health record features, feature 1 and feature 2, and I'm just focusing on 2 so that we can visualize it very easily. And in this kind of picture in the upper left, what I'm showing is examples. So each dot is a different electronic health record located according to its 2 features. The gray dots are unlabeled electronic health records, and the red and blue dots are ones that have been labeled by the human experts. So, for example, maybe red indicates disease and blue indicates healthy. So given those few labeled examples, there might be a best linear classifier, like I'm showing with this dashed green line. And the way learning and training will proceed is that in passive learning, the system will just retrieve another unlabeled example at random from the pool of electronic health records. So maybe this dot that I've circled in purple here, and it will repeatedly do that. Just pick another random example, ask the human expert to label it, and we'll get some sort of performance out of our system. As we get more labeled, or as the machine gets more labeled examples, the test error rate will go down. And that's what I'm showing you down in the lower right. This is the actual test error decay as a function of the number of labeled examples in a setting where we're trying to predict whether somebody has cataracts or not based on about 6,000 electronic health record features. And we're using linear classifiers, just as I'm sort of depicting up in the upper left. So what does active learning do? Active learning says, well, maybe the system should try to decide which examples it's least confident about. And one heuristic for that is to look at examples that are close to the current decision boundary. So I've circled one of those examples in orange here. And this is how active learning would work. It would select a sample like this, ask for a label, update that linear classifier, and repeat. And what that can do is drive the error down much more quickly. In this particular example, we saw about a 3x improvement. So we can learn a very good classifier using 3 times fewer examples with an active learning method as opposed to a passive learning method. So that can be a pretty big gain in terms of the time and effort required from those human experts to train a good classifier for this task. Okay. So I just want to kind of mention what are the challenges or hurdles here to active learning. It sounds great. Why don't we just do it all the time? Well, there are really three reasons. First of all, active learning is combining data fitting and data collection. And this requires sort of an interactive computing architecture. And so it's not as simple as just coding up your favorite algorithm in Python and applying it to a fixed data set. The data set is being curated as you go, and so you really need a kind of real-time interactive computing software system. And we and other groups have developed systems like this. We have one at Wisconsin called MNIST, which is an open source software system that helps people prototype active learning algorithms. The second challenge is that, as I mentioned, this is a closed-loop feedback system, and that means that algorithm design and analysis is a lot more challenging than it is in the traditional passive learning setting. And then finally, and this is something I'll be talking about later in the talk, is that the sort of data or example selection in active learning is based on the particular form of prediction model that you're considering. And so because data selection is based on the model specifications, if there are misspecifications, and you have inductive bias in your system, for example, you're choosing to use linear classifiers, if those linear classifiers are sort of not very accurate models for the problem at hand, you can really run into problems in active learning because you're trying to leverage that structure so heavily. So that's just a kind of famous quote everybody's probably heard, essentially all models are wrong, but some are useful, by George Box, who was a professor here at Madison. And what I'm saying is that that problem of models being wrong is especially problematic in the setting of active learning. Okay, so maybe I'll just pause there. I don't know if there are any clarifying questions have come up in the chat or anything. I could take them or I can just keep going. Good. Well, I'll continue, and again, happy to take questions as we go or end at the end. So to understand active learning, maybe it's good to just start off at a very, very simple setting, the simplest perhaps, and that is learning a one-dimensional binary classifier. So what I'm showing you here are examples in a one-dimensional feature space, and those are unlabeled, but let's suppose those are the labeled examples. Okay, now we have labeled data, and if I asked you where should your decision boundary go, we can just see it right there. It should go right in between the red samples and the blue samples. So how do passive and active learning compare in this very simple setting? Well, the active method that you would naturally consider here is something like binary search, and that's what I'm showing over on the right, and I'm comparing it to just randomly selecting examples for labeling on the left. And so what you can see is after a small number of samples, the binary search has really localized where that decision boundary should be, whereas the random passive sampling has a lot of sort of uncertainty left in it about where that decision boundary should really be placed. And so in this setting, it's very simple, but we can see that binary search quickly finds a decision boundary. And if I have n labeled examples, then the sort of error rate of passive learning will decay like 1 over n, 1 over the number of labeled examples, whereas in active, it's decaying exponentially with the number of labeled examples. So there's this huge exponential speed up in active learning compared to passive learning, and that's something that we'll see holds more generally in certain cases. So to kind of generalize this idea of binary search and so forth to higher dimensional spaces and other function spaces, there's a nice idea which is called disagreement-based active learning. And I'm going to illustrate it in the context of learning linear classifiers. And to begin with, we're going to look at a situation where our training examples are uniformly distributed in the unit ball. And we're going to look at linear classifiers passing through the origin. So there is a linear classifier passing through the origin. Linear classifiers just split the ball into two hemispheres. And we don't know which linear classifier is the best one. It could be at any orientation. So the idea is, suppose that we had some labeled examples like the ones I'm showing you here. With those labeled examples, you could say, well, which of all of those possible linear classifiers or orientations are consistent with these data? And so it would be linear classifiers like the ones I'm showing you. Based on those data, we could accept any one of these as a good separator of the labeled examples we've seen so far. So we can use that to sort of partition the data space into two components. A component where all the classifiers agree, and that's the gray region you see here, and then a component of the data space where there is some disagreement among the classifiers. We call that the region of disagreement. And what it means is that one or more classifiers disagree with the majority of classifiers in those gray regions. So in the green regions, that's where we might get some new information to refine what we understand about the set of classifiers that might be good for this particular problem. And so the idea is we'll draw another set of samples. So those are black dots, and we have to decide which of these we want to label. Labeling examples in the gray region doesn't help us at all because we already know that the true classifier won't be in that region. All of the classifiers that are consistent with the data agree in the gray region, so we don't bother with those. We only label examples that are in this region of disagreement. So these two in this example, and then we refine what we understand about this region of disagreement, and we have a new region that's smaller than before. And the idea of disagreement-based active learning is to iterate this process, to efficiently learn a good classifier. And by efficiently, I mean by labeling a small number of examples rather than just picking examples at random to label. We'll only ask for labels on ones that will help us refine this region of disagreement. So the upshot of all this is that there are ways to design classifiers so that if you want to find a classifier whose error rate is within epsilon of the optimal linear classifier, so I'll call that epsilon optimal, passive learning would require order d over epsilon labeled examples, d being the dimension of the feature space and epsilon being this desired sort of accuracy level. Active learning, in contrast, is also linear in d, but only logarithmic in 1 over epsilon. So we have this log 1 over epsilon instead of epsilon, and that's the exponential gain that you can get through active learning in a situation like this. So the challenge is that I've sort of drawn you what the region of disagreement looks like in this very special setting of linear classifiers passing through the origin in a two-dimensional feature space. More generally, the shape of the region of disagreement is much more complicated in higher dimensions. In fact, it's even more complicated in 2 dimensions if we eliminate this restriction that classifiers pass through the origin. So let's look at a general linear classifier in 2 dimensions. So here I'm showing you a data set. Clearly, any linear separator of this data set will not pass through the origin of the unit ball here. And we can start saying, well, what sort of linear classifiers would separate these data? Well, here's a classifier. This would be what you would consider the max margin linear classifier. This is another classifier that separates those data. Here's another one, and so forth. So all of these are possible classifiers that separate the labeled examples that we've seen so far in this case. And this is what the region of disagreement will look like. So it's much more complicated. It doesn't really have this nice cone-like structure. And so this is sort of the general story. Computing the region of disagreement is going to be computationally expensive. It's sort of a combinatorial object, not easy to get your hands on. And just sampling everywhere in this region of disagreement might even be inefficient in high-dimensional settings. And I'll explain why that is in a minute. So the approach that we're going to discuss is the idea of approximating this region of disagreement. It's a complicated set. So let's approximate it with a much simpler set, and that the form of the simpler set that we're going to look at is a spherical segment. So I'm showing you in the large circle a spherical segment in 2D, and then down in the lower right a spherical segment in 3D, and this idea kind of continues to higher dimensions. So that's the idea. And now to understand this, let's look at the special case of homogeneous linear classifiers. This is the case we were talking about just a minute ago, where the classifiers must all pass through the origin. So there's no offset or bias in our linear classifier. That's a special case. This case was studied by Nina Balkin and Phil Long. Nina was a professor at Georgia Tech for a while, so probably many of you know her. And this is a really beautiful work that kind of exposes a super interesting phenomenon that's relevant for learning linear classifiers, and that is that high-dimensional balls have most of their volume near the equator. And because of that sort of effect of high-dimensional probability theory, that sort of drives what Nina did in her work. So here's the idea. The problem is that if we kind of just overbound this region of disagreement with a spherical segment, it could be very wasteful. And so let me kind of show you what I mean. So here's an overbounding approximation to that region of disagreement. And you can see it completely covers the green region of disagreement, but it also covers a lot of area that where all the classifiers agree. So we have a lot of volume, in fact, an enormous amount of volume near the equator that's just being collected, and these are wasted samples. We don't need the labels for those examples, but we're collecting them anyway because we're using, say, this sort of overbounding approximation. So in high dimensions, most of the volume is going to be close to the equator. It means that almost a huge fraction, maybe the majority of the labels that we get are all on examples where we already know how to label them. So what Nina did, and this was sort of the key idea in her paper, is she said, well, we need to be more aggressive about how we approximate. We need to localize things a little bit more to reduce this wasteful sampling. And so the idea is to use a spherical segment again, but now one that doesn't completely cover the region of disagreement. And what's done is essentially balancing to get fewer wasted examples near the equator, while at the same time not sacrificing too many of the helpful examples that are in the region of disagreement that's not covered by this segment. And so the upshot of this more aggressive localization is that instead of having a sample complexity or a labeled sample complexity that grows like d to the 3/2, Nina was able to show that she can get the sort of information theoretically optimal dependence of just linear in dimension using this aggressive procedure. Okay, so I just want to reiterate that everything looks pretty simple here in 2 dimensions. We have these nice cones when we're having classifiers that pass through the origin, but these regions of disagreement are much more complicated in general, and that's why we have to use these these approximation techniques. So let's go back to this general linear classifier case. This was something that wasn't covered in Nina's work, and it's important in practice for a couple of reasons. First of all, in general, when we train linear classifiers, we really usually don't insist that they have no bias term. So this bias term B that I'm showing you there offsets our classifier from the origin, and that's important in general. Also, another thing that we can study when we look at more general linear classifiers is that classes are often very imbalanced. In the setting that we were just looking at before, with the classifiers going through the origin, the 2 classes were perfectly balanced. One class was in one hemisphere, the other was in the other hemisphere. And that's meaning that you'd have equal number of examples from both classes. So because of class imbalance, which happens a lot, for example, there are many more healthy people than diseased, thankfully, we need to be able to handle that kind of bias in the prior probabilities of the 2 classes too. And this more general form of the linear classifier in this model that we're looking at will help us do that. So the challenges, though, that come up when we look at this more general setting are that the region of disagreement can be much more complicated, even in 2 dimensions, as we talked about. And then kind of specifically what that leads to is that the fact that spherical caps of high-dimensional spheres are much smaller in volume than segments that pass through the equator. So because we're offset from the equator now, everything will get even more complicated than it was before. So we need to figure out a good approximation to the region of disagreement in the general linear classifier setting, and that's more complicated than it was when we were looking at homogeneous classifiers that pass through the origin. So this is something that Mina Karzand and I started to look at, and this is how do we approximate a region of disagreement in this general setting with a spherical segment. Showing you the general setting, I'm showing the spherical segment, and the problem again is that there's exponentially less volume in this spherical cap, right? And so what that means is that if we just use a region of a spherical segment that somehow covers a portion of the region of disagreement, if we're not careful, that segment can disproportionately favor the majority class. In other words, most of the examples that we ask for labels for will be coming from the majority class because of the class imbalance. And also because, again, there's so much, the volume decreases so quickly as we move away from the equator, we could potentially be wasting a huge number of samples by sampling in regions near the equator that aren't part of the region of disagreement. So what we need to do is somehow move and design a spherical segment that is as far from the equator as we can make it to better balance the classes and reduce this wasted sampling. And that's just a lot more trickier than it was in the homogeneous case, because in this case, it turns out it really doesn't matter how you orient this segment, as long as it's sort of oriented in a way that passes through the origin and covers a good fraction of the region of disagreement. So there wasn't so much sensitivity there, but it becomes much more challenging and problematic when we're not looking at the homogeneous case, the general case. So here is the solution that we came up with. We're going to construct a spherical segment based on the data-consistent classifier that's closest to the origin. Okay, so I'm going to show you what that one looks like. It's this guy here. So that's a linear classifier that's pushed as close to the origin of the unit ball as we can make it while still being consistent on the data we've seen. And what that actually does is it separates the unit ball into two pieces. And we call this the MaxiMin volume separator because it has the effect of maximizing the minimum volume of the two pieces. In this case, the minimum volume is the upper part, which is a spherical cap. And it turns out that's the right trick, or at least it's a right prescription that will work. If we use this spherical segment, then it better balances sampling between the two classes, and it reduces wasted sampling outside of the region of disagreement. Because even though it looks like there's a large portion of this segment that's not overlapping or intersecting with the region of disagreement, that region, which is sort of in the right here, is away from the equator. So even though it looks large here in high dimensions, that's a relatively tiny area. So this is sort of the result, then, this MaxiMin volume separator, and basing our spherical segment approximation on that, and then sampling that region is the key idea. And if we assume that our learning algorithm is initialized with at least one example from each class, that sort of just avoids a necessary search to find at least one example from each class at the beginning. But as long as we have that initialization, then what we can show is that we can learn an epsilon optimal classifier with the optimal sample complexity, both in terms of dimension and in terms of the accuracy epsilon. Okay, and so that's sort of what we know about linear classifiers. I would say that, by and large, a lot of the theory and algorithm for active linear classification is pretty well developed at this point. There's one open problem I'll just leave you with, and we can talk about it afterwards if people like, is just efficient methods for finding this MaxiMin volume separator. It's naturally posed. It's not really a nice convex optimization. I think there are good ways to kind of solve this. I've talked with some people about it, but I don't know yet what's the most efficient way to find these maximum volume separators that we use for this construction. So that is what I wanted to say about linear classifiers. How are we doing? Good. Right. Any questions now, or I can move on to the next section of my talk? Okay, I will continue. So that's great. Linear classifiers are good. They're easy to understand. They're easy to interpret, but they're certainly often not what people are using in practice. And there can be especially problems with using simple models like linear classifiers in active learning, because these models can really break down the active learning process. So I'm showing here again this example where we have two features in a feature space, a linear classifier. So that's the best linear classifier we could find in this setting. So there is no linear classifier that's consistent with all the labeled data. And here's a suboptimal linear classifier. This one will not have, it will have a larger error than the other one. And so the problem is that when we fix ourselves or force our active learning algorithm to use a particular model like a linear classifier, that introduces sort of a bias into the whole procedure. And standard active learning algorithms might perform no better than passive because of this, because the model might not match reality. And they can even, if we're being aggressive, like we were just talking about before, with these approximations to the region of disagreement and so forth, might even converge to suboptimal solutions like the one I'm showing on the left. So that's a problem. And the basic idea is active learning suffers when models are misspecified. So that suggests moving to a more non-parametric kind of setting. So we can use non-parametric models that could learn arbitrary kind of decision boundaries. So I'm showing you here with the same set of examples where a linear classifier can't classify the examples correctly, but something nonlinear could, as I'm showing on the right. Maybe we can try to develop active learning methods for more flexible models like that. And there has been work on this by myself and others. And basically, the past work has been theoretical. It indicates that there's some potential for active learning in non-parametric settings, but there were no practical sort of methods that were coming out of that work. So what I'm going to talk about in the rest of the talk here is how we can develop sort of practical active learning methods for non-parametric models. And in particular, again, this is work with Mina, we're asking the question about, can we develop active learning algorithms for popular modern classification methods like kernel methods and neural networks? And so we're going to focus particularly on single hidden layer neural networks and kernel classifiers, which both have this sort of linear, nonlinear, linear type of structure. And we have some nice results for how to do active learning in these settings. And these are completely flexible. They could handle essentially arbitrary classification problems as long as we have a wide enough neural network or a rich enough kernel and reproducing kernel Hilbert space. Okay, so how do we get started on thinking about this? Well, I think the right perspective is one that's been popularized lately, and that is to look at generalization error from a function space point of view. So what I'm showing in this picture is the classical sort of bias variance trade-off. And on the vertical axis, we have error, and on the horizontal axis, we have model complexity, or the number of parameters in our model. And so the usual story is that, well, if we try to fit our model perfectly to the data by giving it enough parameters or degrees of freedom, we can get the training error to be very small, but we might suffer a very large test error. In other words, we're overfitting the data. And so the classical story of regularization and so forth would be somehow to balance this and hopefully find the bottom of that test error curve, something that gives us the lowest test error. So that would mean not perfectly fitting the training data. But that's not what people are doing with deep neural networks and other methods these days. They really just train to near zero error. And so a lot of people have been studying this, and there's this nice work by Misha Belkin and his colleagues, which kind of popularized this idea of the double descent curve. So this is how it might look if we thought about neural networks with a certain number of parameters. As we increase the number of parameters beyond sort of the number of training points, which is the so-called interpolation threshold, we'll actually see sometimes or often that this error, the generalization error, will actually decrease as we go further into further overparameterization. And what's really going on here, the key idea is that we shouldn't be obsessing about the number of parameters. Rather, we should be focusing on the function space associated with the overparameterized models and think about minimizing the norm of those functions subject to data fitting. And if we do that, we can have a huge number of parameters as long as we control the complexity of the resulting function by considering its norm in whatever function space it sits in, subject to trying to fit the data. In other words, trying to get zero training error. And so this is sort of the motivation for our active learning heuristic, which we call MaxiMin active learning. And let me explain it, and this is kind of an important slide, so I'll go kind of slowly to make sure everybody gets the idea. So U star is going to be an unlabeled example that the machine is going to select to ask for the next label. And so what is this optimization doing? So the set big U is the set of all possible unlabeled examples it could select from. And then what I have inside this min is the norm of the new function that we learn if we incorporate the example U. Now, if we add U to the training set, we don't know whether that should be labeled +1 or -1, so we consider two possible new learned models. The learned model adding U, assuming it has a negative label, and the new function that we learn by adding U, assuming it has a positive label. And then we look at the norm of those two new fitted functions, and we look at the min of those two, and then we max over all samples. So essentially what we're doing here is we're labeling the example that maximizes the norm of the what you might consider optimistic new function learned by adding it to the training set. And by optimistic, I mean if we add this example, how hard or how much do we have to change our prediction function in order to accommodate that new labeled example? And we can measure how much that changes by the norm, and we're sort of optimistically hoping that our guess at the label, which would be the min of these two here, is correct, and we don't have to do a lot of work in changing our function to accommodate the new sample. So the intuition is that attacking the most challenging examples first, that's what this max part is doing, may eliminate the need to label other easier examples later in the process. And in theory, what we can show is this automatically selects examples near the current decision boundary and closest to oppositely labeled examples. Okay, so let me kind of illustrate this with a simple setting. So let's go back to one dimension. We're looking at a one-dimensional setting, and what I'm showing you here is on the right a piecewise constant function. So the function is valued +1 or -1, and you can see there are three change points in these functions. This would be essentially these are the decision locations of the decision boundary in this classification problem. The two red X's are some initial labeled points. So that's where we kind of initially have sampled. And I'm just going to run a little video that shows you the progression of where this MaxiMin criterion selects samples as we go. And so what you can see, what happens is the process automatically sort of homes in on and focuses on these locations of the decision boundary. And so I'm just looping over this process a few times so you can watch it and see it. But it kind of automatically finds and localizes the decision boundaries. So it's not sampling far away from those decision boundaries too often. And so what we can actually prove is that if we have endpoints uniformly distributed in the unit interval and labeled according to a piecewise constant binary function f with k pieces, then if we run this MaxiMin criterion for active learning using either a Laplace kernel or a rectified linear unit neural network, then that active learner will perfectly predict all n labels after only labeling about k log n of the examples. And so this is sort of recovering the optimal binary search or bisection performance. It's actually a little better than that because we don't even need to know how many pieces there are. This k is just an unknown part of this target function that we're trying to learn. It's automatically adaptive to that too. So it recovers binary search and kind of goes beyond binary search just automatically. The beauty is that we can apply this criterion, in multiple dimensions. It's just an illustration here in one dimension. So here's how it could look in multiple dimensions. I'll just show it in two so we can visualize it. So what I'm showing you on the left there are the kind of interpolation or data, the function fits to 4 labeled data points. The top for a reproducing kernel Hilbert space, Laplace kernel, and on the bottom, a neural network that's been trained to fit those points. And the color that you're seeing in these images is the absolute value of those functional fits. The dark blue is 0. So that would be the 0 level set or the current decision boundary of those two methods. And you can see they're similar for the kernel method and the neural network. So those dark blue portions on the left indicate the current decision boundary. If we apply this MaxiMin criterion to decide where to sample next, the heat maps just to the right are showing you where the MaxiMin criterion is telling the algorithm to ask for a labeled example next. So the bright yellow is where it will sample next, and you see in both cases it's asking for a sample or looking for samples that are in between the closest oppositely labeled pair of examples in the initial training set. So it sort of recovers this kind of bisection-like performance in multiple dimensions. And here's a little video illustrating this. So I have two regions in a two-dimensional feature space, examples uniformly distributed over this feature space. On the right, labeled -1, on the left, labeled +1, with this sort of sinusoidal-like decision boundary. And what happens is the initial part of the algorithm just sort of starts randomly sampling until it gets oppositely labeled examples. Then it kind of does a binary search, and then it sort of stitches along automatically, kind of tracking this decision boundary very efficiently. So in multiple dimensions, we sort of have this multi-dimensional version of a binary search going on. I'll just show some MNIST experiments to show how it looks in practice. This is using the Laplace kernel for the task of classifying whether a handwritten digit is either from 0 to 4 or from 5 to 9. So we've kind of reduced it to a binary classification task of that form. And we're comparing, looking at the training and test error, both for random, passive learning, and then the MaxiMin criterion, active learning, and then a data-based version of MaxiMin, which I won't have time to go into, but it's just designed to do a little bit better at early stages of the process when you have very few labeled examples. But what you can see here is that both in terms of training and test error, the MaxiMin criterion at active learning is doing much better in terms of reducing the error quickly. So we can train more quickly and we can get better test errors. And in this case, we're seeing about a 3 to 4x improvement in terms of the number of labeled examples that we need in order to design a good kernel-based classifier. And so I should just kind of mention that, you know, the theory of some of the stuff I showed before talked about these exponential improvements. In practice, you know, real life is more complicated than some of those idealized settings. So getting these kind of like, you know, 3 to 4x improvements is kind of what we often see in real world problems. And that's still very substantial because that means, you know, a big reduction in the amount of human effort required to train these systems. So kind of what goes into proving something about this kind of bisection behavior involves looking into the structure of the modeling spaces. So in the kernel case, the representer theorem shows us that the optimal interpolator, of course, is a superposition of kernel representers. I'll go over this idea of representer theorems in a bit of detail in a minute. The metrics associated with that kernel function, and it has a special block diagonal structure in the Laplace case. And we can use this then to show that the increase in the kernel norm is maximal at the point between oppositely labeled points. So that's exactly what gives us this bisection performance. In the case of rectified linear unit neural networks, things are a bit more complicated. We actually use a new neural network representer theorem that I'll tell you about, but this shows that in 1D at least, the optimal neural network is equivalent to a classic linear spline, and it turns out that the neural network weight norm then corresponds to a total variation norm of that spline function, and the total variation norm increases the most when a new example is added at the midpoint between the closest oppositely labeled examples, which again is what produces this bisection performance. So we understand this very well in these two cases, and the key to understanding both of them is looking at things through this lens of representer theorems. So in the last part of the talk here, I'm just going to kind of talk about representer theorems and specifically talk about these new representer theorems for neural networks. Okay, so the classical representer theorem is telling us that solutions to certain learning problems in infinite dimensional function spaces can be expressed in terms of finite dimensional parametric functions. And this goes back to the classic work of Grace Waba, a colleague of mine here at the University of Wisconsin, in her famous paper, Smoothing Splines. Since 1970, reproducing kernel Hilbert space representer theorems have had incredible impact and widespread use in machine learning with kernel learning methods, and that really kicked off in the early 90s with support vector machines, and active area of research today. More recently, people have been looking beyond just Hilbert spaces to Banach spaces and things like TV regularization and atomic representations. And our work on neural network representer theorems falls into that more modern category of representer theory. So just to kind of recall, here's the classical representer theorem for a reproducing kernel Hilbert space. If F is an RKHS equipped with some norm and a kernel K, then for any training data set and any loss function and any function minimizing this regularized empirical risk, so we're looking at minimizing the sum of losses on our training data plus a term which is a weighted version of the RKHS norm of our prediction function F, those solutions admit representation in the following form that I'm showing, where F is a linear combination of the kernel function based at each of the training examples, xi. And these alpha i's are the dual variables that you're probably familiar with if you've looked at RKHS representer theorems. So that's the classical representer theorem. It basically tells us that this infinite dimensional function space optimization and learning problem has a solution which is parametric. We just need to determine these n numbers, alpha 1 through alpha n, where n is the number of training examples that we have. So my student Rahul Pari asked the question of, is there a representer theorem for neural networks? And the answer is yes, there is, but it's not in a Hilbert space. And so I'm just going to kind of give an informal statement of this representer theorem, and then I'll dive a little bit into the details. And I think I'm doing pretty good on time. I think I have about 5 more minutes, and I should be able to wrap up. So the neural network representer theorem says that, and I'll tell you what this Banach space and norm are in a minute, but there's a Banach space and a norm such that for any training set and any convex and coercive loss function L, there exists a solution to this infinite dimensional Banach space optimization learning problem that has a representation which is exactly in the form of a single hidden layer neural network. So that's what I'm showing down at the bottom there, where the phi function is the activation function, and k is the number of neurons, and the number of neurons needed in such a solution can be less than or equal to n, the number of training points. So it's very analogous to what we just saw for RKHSs. So here is I'll kind of just spend the last few minutes diving in a little bit to what are these Banach spaces and what's the connection to neural networks. So the Banach space is a set of functions mapping RD to R that have the following bounded norm. So that we're looking at the function f, then we apply an iterated Laplacian operator. This is a differentiation step, and then a filtered Radon transform. And so what this Laplacian is doing is measuring the roughness of the function, if you will, and we're looking at the roughness of the function in the Radon domain. And I'll explain why that's the appropriate domain to consider the roughness or irregularity of functions. What we show in the representative theorem then is that if we try to minimize this norm subject to data fitting, the solution is a network. And these activation functions include the ReLU function. So you notice the function spaces are indexed by integers m. M equals 1 corresponds to the case where we just apply one operation of the Laplacian operator, and it turns out that the solutions have the form of rectified linear unit neural networks. If I increase m, essentially the activation functions are higher power versions of truncated power functions, quadratic, cubic, etc. And I'm showing you what those look like in the bottom right corner. So I want to say a little bit about the function norm and weight norms and generalization bounds. So if I have a neural network, a single hidden layer neural network of that form that I just described, the Banach space norm is exactly equal to a network path norm. And this is sort of one of the key connections between the neural network weights and these function space representations. Moreover, we can show that the Banach space norm essentially controls the generalization error. So if I say minimize data fitting subject to forcing the function in that Banach space to have a norm less than or equal to some value capital B, then the generalization error bound is proportional to that bound on the norm. So why the Radon transform? So I think I'll just take a couple of minutes to explain this, and then we can stop for questions. So the key idea is that neural network neurons are what are called ridge functions. So here I'm showing the rectified linear unit activation function. And if I look at that, what that generates then with a two-dimensional input to that neuron, it gives me a ridge-like function that I'm showing on the right there. Ridge functions are parameterized by two things: their orientation or angle and their offset. And so we can look at for example, here I'm looking top down now at that same ridge function where the orientation is 0. I can rotate it. Here's the orientation at 3/4 over pi, and then I can translate it. That's what the bias or offset is doing B. Okay, so those two things, kind of the functional form, for example, this piecewise linear form here is dictated by the activation function, but then the weights of the neural network and the biases are telling me the orientation and offset. And so for studying multidimensional functions at different orientations and offsets, the Radon Transform is sort of the key tool that we would use. So what it basically does is it looks at a multidimensional object and its projection into different orientations. And so we have different orientations, and then the sort of dimension in that projection is the offset. And this idea goes back a long time. Radon transforms and ridge functions, starting off with analyzing plane waves back in the 50s. The term ridge function was coined in the context of tomography back in the 70s. Radon transforms are central to the analysis of ridgelets, which were popularized in the 90s. And then more recently, Greg Onge and his collaborators made this connection between the Radon transform and single hidden layer ReLU networks. The main sort of thing that we bring to the table in our work is, rather than just focusing on how well we can approximate functions with ridge functions, we look at exactly what kind of functions are learned by fitting neural networks to training data. And so that's something that is kind of the learning from data version as opposed to the approximation theoretic question. So here are just a few pictures to illustrate what's going on with this norm and the Radon transform. So here's a ReLU function. It's a special type of ridge. If we apply the Laplacian operator, which is basically taking second derivatives, then we get just a line when we apply that to the ReLU neuron. And that line is in the orientation of the activation of that ReLU. And then if we apply the filtered Radon transform, what that does is it basically looks at that in terms of orientation and offset, and we'll just get an impulse exactly at the location of the orientation and offset of that original ReLU neuron. So it kind of these two operations sparsify a neuron and just give us a Dirac delta in the Radon domain. So as I just said, more generally, differentiation, the iterated Laplacian annihilates polynomial surfaces, leaving only linear boundaries of the activation thresholds. And then the filtered Radon transform extracts the orientations and offsets. And then finally, this L1 norm is basically measuring sparsity in the Radon domain. So here's how it looks for a 7-neuron network with rectified cubic units. So that's what I'm showing at the left. You apply the Laplacian twice, you'll get the black lines that I'm showing in the middle. Those are the activation boundaries of each of the neurons. And then if I take the filtered Radon transform, I get this map that you see on the right, which shows impulses exactly at the offsets and orientations of all of those 7 neurons. Right, so I think I'm just going to pass over this because I think we're a little short on time. I'm happy to talk about what goes into the ingredients of proving that representative theorem, but we kind of look at it through the lens of Green's functions and measure theory and the classical measure recovery problem, which goes back to the 40s. And you can put all that together in this context and see that the solution to these optimization problems are single hidden layer neural networks. And so I'll just wrap up with a couple of takeaway messages. We talked about how these nonparametric learning problems with this particular Banach space structure have sparse solutions, which are neural networks. And one thing we can do with this then is look at what happens when we add a training example. How does that affect and increase the norm? And that's the key behind our active learning heuristic. A couple of things I didn't tell you about is that this regularization actually is equivalent to a form of weight decay in SGD. And in the one-dimensional case, reduces to classic polynomial splines. And I'll just show you a little example here of fitting 6 points with a cubic spline, fitting them with a rectified cubic neural network using SGD and weight decay. You see it exactly recovers the cubic spline. But if I don't use weight decay, I can actually learn an interpolator that is more complex than necessary. For example, this one has an extra bump here. So there does seem to be something important going on in this connection with weight decay in these function spaces. And I'll just wrap up there. I won't go over what I already told you, but a few open problems are finding efficient methods for computing this MaxiMin volume linear separator, and then also efficient methods for the MaxiMin criterion in nonparametric setting. and maybe trying to extend representer-like theorems to deeper neural network structures. And those are a few of the papers that relate to what I covered today. So I'll stop there. I think we're doing okay. Guess we have a little time for questions.
Yes, this is great. Thanks a lot. Wonderful talk, and thanks a lot for all the sharings. And so I guess there are a bunch of questions. We'll start with one question. It has lots of likes, so a very interesting question about how does active learning deal with noise? A model could ask for a label of a noisy data point and give it full weights, and it would go to a normal data point. It will readjust itself and move away from the optimal solution. So I guess this is about how active learning deals with noise.
Great, yeah. Yeah, so the question is, what about noise? And that's a great question. Active learning methods can be noise-seeking in a way, right? In some ways, we're trying to measure how certain or uncertain our current prediction is about an unlabeled example. And one reason a prediction might be uncertain is just because there may be a lot of noise in our labeled data. And so that is a problem. There are a lot of different ways people can deal with it. I've been sort of focusing more on the case where we're thinking about not having a lot of labeled noise, but there are ways to robustify all of the linear classifier stuff that I talked about. And in the nonparametric setting, there are also ways that you might make the methods more robust if you believe there is potential for labeled noise or outliers or whatever in your training data. On the other hand, if we think about a lot of settings like image classification, where we really don't think there's too much label noise, we might really want to try to fit as well as we can to the labeled data we have. And so what I was describing would fit that kind of scenario very well. So roughly speaking, you can do a little bit of, to handle noise, a little bit of voting over multiple examples in regions of interest, and then using some sort of localized majority voting to kind of mitigate the effects of noise. So that's kind of, in essence, one of the things that's used. Another thing you might do is, rather than just having a single classifier, you might learn multiple classifiers, possibly with thinking that some of the labels you're getting might be mislabeled, and then you could generate sort of an ensemble of classifiers and then average your predictions over them. That's another way you could reduce some of the noise. So it's a great question, and how to handle it really depends on the particulars of the sort of model structure that you're using. So I could follow up with that person offline if they want to chat more about it.
Great, that's great, thanks. I guess there are a bunch of questions. Depending on how much time we have, I think we can do a selection of them. This is great response, I think, from the audience. So Professor Xiaoming Huo, I want to ask, out of curiosity, in your result regarding neural network Banach function space representation theorem, this is the end of your talk. Are you considering to generalize to the cases such that the representation function is a multi-layer neural network instead of a single-layer neural network?
Yeah, so that would be great to be able to generalize this to multi-layer hidden neural networks. So far, I have to admit, if that were easy to do, we might have tried to do it. It seems not too easy to generalize this to multi-layer settings. The compositionality that is so powerful in multi-layer neural networks is what makes it kind of more difficult to analyze. There's just a lot of dependencies through the layers that makes it non-trivial, possibly impossible, to extend these representer theorems to multi-layer settings. But it's something we're thinking about, and I think it's a great open question. It might not look the same. They might not have the same kind of characterization that we have for single hidden layer neural networks, but maybe there's something else that would be helpful in the multi-layer setting, but it's an open problem.
I see, thanks. There's a question about, would you do this before splitting data into training validation test set? Or do you advise doing active learning only on a training set to keep validation test set representative?
Yeah, so usually, so that's right. We would do the active learning and sort of selective sampling only on training, but for test and validation, we would always have like a nice unbiased holdout set. That's exactly right. That's what we would normally do. The one thing I will say, though, is that because active learning can give you, potentially very large speedups in some nice settings, exponential speedups over passive learning. There are situations where you could learn a very, very good classifier, but you'd need an enormous amount of test data to even estimate the test error to the accuracy that it's achieving. And so you can't always, in other words, your holdout estimate of the test error is only going down like 1 over the square root of n, right? But the actual error of your classifier could be going down much faster in active learning. So there's a little bit of interesting fact there.
Mm-hmm. Yeah, exactly. There's a related question, I think, about labeling. So this question asks, do we label the data once, or we continuously label the data as it comes in?
Yeah, so the normal way that there are different ways to implement active learning systems. The normal way we would implement them would be kind of in an online fashion. So we ask our human or our crowd to label some examples. We take those labeled examples, try to learn a good predictive model, use that learned predictive model to select which examples we'd like the person or crowd to label next, and we repeat that process sort of in a sequential online fashion. One of the practical challenges that comes up is that once a person or crowd delivers some labeled examples, you have to retrain your models. That takes some time. And it might take more time than a few hundred milliseconds. So people might be ready to label more examples before you've been able to completely update your model. So a lot of the challenges that go into implementing software systems deal with this, deal with the need to cope for those sort of latencies between how quickly you can update models, how quickly people can label new examples, how quickly you can select new examples for labeling, and so forth. So all those things are happening in parallel, and they all have their own latencies. So that's a challenge that comes up in the actual implementations.
Okay, makes sense. There's a question about the theory, I guess. So ask about the active learning bound of order d divided by log 1 over epsilon assumes that the distribution is special, uniform or isotropic log concave. Is this correct? Or arbitrary input distribution? Oh, this is correct. Great.
Yeah, that's correct for that case. So in those theoretical analyses of the linear classifier, we're assuming uniform or isotropic distributions. The one thing that our new analysis kind of allows us to cope with is situations where we have these inhomogeneous linear classifiers and also potentially large class imbalances. I think that's important because these new ideas might also allow us to be a bit more robust to some of those distributional assumptions that underlie the theory, although that's just sort of speculative at this point. But there is something sort of intuitively appealing about this MaxiMin volume separator as the basis for deciding where to sample in a general linear active learning problem.
Great. So there's actually a related question on this maximum volume approach. So the question asks, could the maximizing the minimum volume approach be favoring the majority class in some classes? I assume it is better balancing volume allocated to both classes, but no mathematically trying to achieve an exact balanced volume.
So I'm not entirely sure I got the question. What was the last part there?
So I guess the first part is asking, could the maximum minimum volume approach be favoring the majority class? And so the second part is, I assume it is better balancing volume allocated to both classes. And so is this done mathematically trying to balance the volumes for the both classes?
Yeah, so that's a great question. So first of all, since we don't really know where the two class conditional distributions are supported, say in the unit ball and those examples, our sort of region that we sample from in this spherical segment is just an approximation. And this MaxiMin volume linear separator is just an approximation. We don't really know that that's where the two classes are separated. So the idea, though, is that particular choice of the MaxiMin volume separator is at least one that kind of gives as much volume on the side of the minority class as possible. And then what we're actually balancing in our analysis is the trade-off between sampling in volume where there is no disagreement among the classifiers, so outside of the region of disagreement, balancing that with covering as much as possible the region of disagreement and not missing important regions of it. And so those are the two things that we can actually balance. How much we're sampling within the region of disagreement versus how much we're sampling unnecessarily outside of it. But roughly speaking, the intuition is that this is also helping to balance between the two classes.
Okay, great. So I think given the time, maybe can we take two more questions? I think one question is asking predicting possible counterfactuals for each label value sounds computationally expensive, especially for every data points in the training set. Is this a concern in terms of runtime or memory?
Totally, yeah. That is, making these things practical. In principle, let's just take the neural network case. We would have to retrain a neural network twice. I mean, maybe we can warm start it from our previous solutions, but still, it's a lot of retraining, and we have to do that for every unlabeled data point. Now, we can obviously reduce this by having some heuristics to, first of all, thin out the herd of all the unlabeled points. We kind of know where we think they might be, or where the most important ones might be, so we might be able to cut down there. And then in terms of retraining, maybe we're looking at things like heuristics, like just looking at the norm of the gradient at each of those new points, which just involves one gradient computation as opposed to fully retraining. And there's some reasons to think that that might be a very reasonable and it maybe even provably good approach. Kind of connects a little bit to things like neural tangent kernels, but also relates to some other sampling methods that are used in other adaptive situations like multi-arm bandits or linear bandits and so forth. So there's some good ideas, I think, out there for possibly making these more computationally feasible.
Great. I guess the last question, which is summarized from a few questions, is asking about possible references. So I think audience are interested in seeing papers related to your presentation today, so they're interested in reading more details. I think you probably provide some on the last page of your presentation.
Yeah, the last page in particular has 3 papers related to this, and in those papers there are a lot of references to other important things, and I think I sprinkled a few other references in throughout the talk, but if people have questions or would like pointers, they're more than welcome to follow up with me. And I'm happy to share my slides too. I don't know if they're something you guys would want to, I mean, we have the video, but I can give you the slides too.
Oh, that'd be great. Yeah, we'll follow up on that. I guess audience are also interested in seeing if there's any introductory reading materials and references for active learning in general, and how to differentiate active learning from the other lines of literature such as incremental learning and so on. So is there any basic references on these topics?
Yeah, there is a kind of monograph or book written by a guy who was a graduate student back in the day here at UW-Mass, and his name is Burr Settles. I think I'd probably reference that in some of these papers, but that's one good sort of overview kind of at least what people were thinking maybe about 8-10 years ago. I don't know if there's a really great sort of up-to-date survey paper on active learning. I might have some kind of overviews that I use in some lectures. If somebody who's interested wants to follow up with me, I could send them some pointers to the Settles monograph and then also to maybe some notes I have that might be helpful. It kind of depends whether you're interested in the theory part or the more practical aspects of it.
Yep. Great. I guess that's pretty much all the questions from here. There's probably more clarification questions and so on. I guess we could probably send these to you as well. Given the time's sake, I think we're a little bit 10 minutes past 1 hour. So I guess that's pretty much of the time now. Thank you so much. Thank you so much again for all the wonderful talk and answering the question. This is really great research. Thank you.
Great. Yeah. Thanks again for the invitation to speak, and thanks for all the great questions and listening in. And if people want to follow up with me, I think my email is also on the first slide, so you know how to reach me.
Okay, wonderful. Thanks a lot.
Okay.
A virtual applause. Thank you.
Yeah. Okay. Bye-bye.
Bye.